Well, I hope you've made it successfully through 2.1. Remember to review all those every day. You've got to remember some of those rules, and we're going to add some today. Some rules for differentiation. This is where things get even more serious and more important. And you must get things done memorization-wise early, or by section 2.4 or 2.5, you'll be in serious trouble. Sorry, but that's the way it is. You have to memorize these rules. So what are we going to look at? The constant rule, finding the derivatives, the power rule, and this is extremely important. This has to be so good you can do it backwards and forwards. The constant multiple rule. Once you get the power rule, the constant multiple rule is just a small extension of the power rule. Sum and difference rules, something you would do normally without even thinking about it. So that's not a big deal, frankly. And using the derivatives, of course, to answer questions about real life situations. That's what you're here for. So first of all, the constant rule, and I'm going to double check, make sure my pen is ready to go. Yeah, looks good. All right, what's the constant rule? You found derivatives already using the limit process, but you already know how tedious that darn thing is. And we are moving to something that'll help make it much simpler if you memorize the rules. So you can calculate the derivatives without the direct use of limits. Now, the limits, of course, are in the background, but you don't have to use them if you know these rules. Here's the first rule, and it says the derivative of c, where c is some number, put any number in you like, equals 0. So what's that mean? Okay, well, let's take a look here. Let's suppose let's start with a function. Let's suppose that function is very simple. Let's just say it's a 4. Now remember, that's the same as saying y equals 4. No different. And we're going to take the derivative of that function. So we're going to take the derivative of y with respect to x. And that dx on the bottom is not a big deal. We're going to expand on that later, but that will be in its own time. Now, the derivative of a constant function, and this means that the y values in this function are always 4s. The derivative is 0. Why is it 0? Well, there's several ways you can look at it, but remember, calculus is all about change. And if y is always 4, there's no change in the y value. And we're talking about changes in the y value. So anytime that you've got a constant function like this, even if it's 14 or 143, the derivative is still 0, because there's no change in y when you go from one point to another. Here are some examples. Here's a function, constant function. The function value is always 7, so the derivative is 0. Next, this function always has a value of 0, so the derivative, and these are two different ways of talking derivative, dy dx or f prime of x, either one. You always get 0 because it's a constant function. Next, another constant function. The y value is always 2 no matter what. So the derivative, here's another look, equals 0. And next, we've got g of t. So we're throwing in a different letter instead of f all the time. And we're throwing in a different variable too. Excuse me. It's not always x, it could be t, it could be almost anything. The point is, the constant is always -3/2, the constant function. So the derivative is 0 again. Next, the power rule. How does this go? Well, this is what it looks like. You've got a function here, and you've got a coefficient out here. Coefficient, just a real number times a basic function. And what here we've got is variable x to some power. Thus, the power rule. We're going to work with the power, with the coefficient occasionally. And this is the basis for a lot of things you're going to do. So first of all, the binomial expansion process. It's a special case. So take a look at this. Now, if you follow my lead, you might put in your notes x plus h squared instead. And if you follow the sort of parallel here, excuse the pun, it'd be x squared plus 2xh plus h squared. Can you make that translation? All the delta x's become h's just to make things a little bit simpler. That way you don't think of this as being two numbers, but one instead, just the h. Second one, x cubed plus 3x squared h plus 3x h squared plus h cubed, and so on. That's the binomial expansion process, and you might recognize this as part of Pascal's triangle too, if you take the coefficients. Of course, we could add one up here, and I'm going to leave out the delta x. To the first power, which is x plus h. Okay, that was pretty simple, right? Now remember, this is the first power. It's not prime, it's the first power. Next, what's the power rule? The power rule is, here's your basic function, x to some power. To get the derivative, for example, let's use this. Let's suppose f of x equals x, and we'll just say to the fifth power. And we want the derivative of f of x, which we could write as f prime of x, or y prime, or dy dx. Bring that 5 out front. And x to what power? We're going to reduce that 5 because we've sort of used it in a way. Subtract 1 from the 5, and there's our derivative. Bring the 5 out front, reduce this exponent by 1, and there's your derivative. That's simple, but very powerful. If n equals 1, you've got a special case. Now, if you don't remember the special case, that's fine, because if you had g of x equals just x to the first power, the derivative, you bring that 1 out front and reduce the 1 by 1, so this would be x to the 0, but x to the 0 is 1, so this would be equal to 1. In other words, whatever number is out in front is the derivative. So here's one you might want to remember. The derivative of just an x is just a 1. You might not want to memorize that. That's fine. If you do enough of these, you're going to do it by instinct. Next. Now, how does this work in, quote, the real world? Well, the slope of the line of x, y equals x, which looks like this, is 1. Well, remember, oops, y equals mx plus b is the slope-intercept form. And the coefficient of x is a 1, so that's the slope. And the y-intercept, by the way, will be a 0. And you can see where it intercepts the y-axis at 0. And you can see for every x that increased by 1, the y increased by 1. 1, 1, 1, 1, and so on. Now, if you've got that down, and you want to spend a bit of time on that, maybe make an index card or two, here's a wrinkle that could cause you a problem. However, if you change the look of this, make 1 over x to the second as x to the negative 2. Remember, 1 over x squared. If you bring this x squared on the top, you change the sign of the power. The reason you would want to do that is because with the way it looks originally here, you can't use the power rule. But if you change the look, if you rewrite it so it looks like this, you can use the power rule. So what's the derivative of this thing anyway? What is y prime, or the dy dx? Well, bring that negative 2 out front. What's the new power of x? I'll subtract 1 from the negative 2, and there's your derivative. But better written as negative 2 over x cubed. There's the derivative. Don't leave it like this. Write it like this as your answer, okay? Next. Well, not next, but rewriting is the first step in lots of differentiations. Things that, oh no, I don't really want to do this, and I certainly don't want to go back and use the limit process. That would be really annoying. So take the original function, rewrite it if that's going to help, do the power rule differentiation, and then simplify so it looks decent. Remember, the derivative of a function, that's what we're finding. The derivative of this function is another function. So f is a function, and its derivative is also a function. This one's the original function, and this talks about changes in f of x. Now let's use what we've learned so far and find the slope of a graph. First of all, if we want the slopes, and the slopes are how f of x is changing as you increase the x values. So first of all, we're going to find f prime of x, and sometimes I refer to that as dy dx. Same thing. So I'll bring that 2 out front. I'll reduce this power by 1, so there's my derivative, alias 2x. Now what are the slopes? X equals negative 2, x value, and what is the slope here? All we have to do is take that 2x. We're talking about an x value of 2, negative 2, there we go. And what's that give me? Slope of negative 4. How about the next one? X equals negative 1. Slope is 2x. The x value is negative 1, and the slope is negative 2. Next one. How about at x equals 0? 2 times x. X is 0 this time, and the slope is 0. Next one. Can you do this by yourself? I bet you can. Why don't you hit pause and do it? All right, you're back. So x equals 1, 2 times 1. Slope there is a positive 2. And last of all on this one, for x equals 2, at x equals 2, the slope is 2 times 2, and the slope there is a 4. And there's a summary. We'll go through this quickly because I just did it one by one. There's -1, x of 0, and x of 1, and with the slopes on the right, and x equals 2, the slope of 4. This is what it looks like. And what I've done up here is I've put the derivative in, derivative alias slope if you're talking about a graph. Remember, this is talking about how that function f is changing. This one is f of x equals x squared. That's the original function. The slope is 2x anywhere you look. So wherever you want to look, if you want to look here, just check to see what the x value is, put the x value in here, and you get the slope or the derivative. Next, the constant multiple rule. Well, you almost don't need this as a separate rule, but I put this in anyway. Constant multiple rule. So what does this look like? Well, let's use an example. Let's use g. I'm tired of using f. So let's say this is 3x to the 8th power. And we want the derivative of that. So we'll call g prime of x. Now, you would ordinarily, up to this point, bring 8 out front, but bringing 8 out front means you're going to be multiplying the 8 times the 3. So bring that 8 out front, you've got 24. And what did we do before? We reduced the 8 by 1, so there's your derivative. Bring the 8 out front, multiply it times any number that happens to be out here. Before, it was just a 1. Reduce this exponent by 1, and there's your derivative. This is the power rule and the constant multiple rule all rolled up into one, like the example I showed you in a little bit. Let's look at another one. Let's call this one h of x. Not that h, no. This is a function called h. Let's say this one is, say, 9x to the 4th power. So what's h prime of x? Bring that 4 out front, multiply it times the 9. I've got 36. And x to the 4 minus 1 is a 3. There's your derivative. Very simple. Now, here's another one, just to give you an idea of what could happen. So let's see, I've used f, g, h, I, j. Let's use j. So this is a different function. Let's suppose your function happens to look like this. 4x to the negative 5. Just follow the rule. Bring the negative 5 out front. J prime of x. Negative 5 times 4 is negative 20. And now don't subtract 1 from that and get a negative 4. Negative 5 minus 1 is negative 6. There's your derivative. And then, of course, we don't write our answers with negative exponents, so your answer will be negative 20 over x to the 6th. That would be the derivative of j of x. Make sure you understand the mathematical conventions and watch out for the parentheses. So let's go with this one. All right, first of all, we're going to rewrite it. So notice we're going to take care of the 5 and the 2 first. We've got the fraction 5 over 2, And this x power, we don't want x to some power in the denominator, so we'll make this x to the minus 3. There's our rewrite. Now we'll differentiate. Bring that negative 3 out front. So negative 3 times 5 is negative 15 over 2. X to what power? Subtract 1 from that, you've got negative 4. Simplify, negative 5, or 15, excuse me, over 2, and x to the 4th. And there's your derivative. Next, let's take a look at this one. Notice that this one, to the untrained eye, looks like it's almost the same thing. But up here, the 3, excuse me, the 3 is the power of x. Down here, 3 is the power of 2x. So what do? First thing we're going to do is multiply this out. 5 is 5. On the bottom, we have to cube this. So it's 2x times 2x times 2x is 8x cubed. Now we're ready to rewrite this thing. We've got 5/8 and x to the negative 3. Now differentiate, bring that negative 3 out front. I've got negative 15/8 x to the what? Negative 4. Simplify that. Negative 15 over 8 x to the 4th. There's your final answer. Next one. First of all, we're going to rewrite that. Notice that this x down here has a negative exponent. So this is going to make it a little bit easier for us. We've got 7 on the top, 3 on the bottom, and this x to the negative 2 can be written as x to the positive 2 up here. And this is our rewrite, 7/3 x squared, not really different. Now we'll differentiate. Bring that 2 out front. 2 times this is 14/3. X to what power? Subtract 1 from the 2, and you've got a 1. Simplify that, 14/3 x. And there's your derivative. Next. Again, we've got something that, if you're not careful, can trick you. But we're going to rewrite this. So first of all, we're going to multiply, like we did in part B. We've got 7, and on the bottom, we've got a negative 2. Well, that means we should have 3x up here with a positive 2. Well, that looks pretty good. So what do we have? 7 times what? 3x times 3x is 9x squared. Final rewrite on that is 63x squared. Now we're ready to differentiate. Bring that 2 out front, 126. And what's the power of 2? 2 minus 1 is 1. Simplify, 126x is your answer. All right. So those are your answers in a summary form. Next, here's something else you might run into. Square roots, cube roots. Oh, not too thrilled about that, are you? Let's take a look at this. Another way of writing the square root of x is x to the 1/2 power, because the number on the top of the fraction in the exponent means power, and the number on the bottom is the root. So this would be the second root or the square root of x. So if you see something like this, rewrite it like that, and then you're ready to differentiate. Bring that 1/3 out front, and so on. Oh, let's go ahead and do it, right? So what would y prime be? Well, alias dy dx. So you bring the 1/3 out front, x to what power? All right, how good are you with fractions? So sneak off here. What's 1/3? What am I going to do with that? Subtract 1. What's 1? 3 over 3. What do I get? Minus 2/3. Did you get that? I hope so. So let's simplify that. We've got 3 on the bottom, 1 on the top. Since we've got a negative exponent, that means x to the 2/3 down here. Now what does that mean? Okay, that means the 2 means the power, 3 means the root. So how do we write that? Go 1 on the top. There's our 3 that we had over here. Now what do we have? We have x squared and the cube root of that. There's pretty much your final answer. We could possibly do something else, but I'm not going to push you that far. Another one would be like this. There's your power on the top, your root on the bottom, and because it's in the denominator, it'd be a negative 4/3 instead of just 4/3. Remember, this could be written first. You might want to do this first. 1 over x to the 4/3, and then change it to this, and it's ready to take the derivative. All right, let's see how this works. First of all, rewrite this friend of ours, x to the 1/2. Now differentiate. Y prime, bring the 1/2 out front. X to what power? Remember, it's 1/2 minus 1, or minus 2 over 2. So you have minus 1/2. Okay, that's not the way you're supposed to write it, is it? First of all, that negative exponent means you've got 1 over 2x to the 1/2 power. Final writing, y prime equals 1 over 2 square root of x. Now you don't need the 2 up there. That's just to remind you that that's where it comes from, the 1/2. Next, I'm going to have to clear this because I've used up some space here. Okay, next one. So first of all, we're going to rewrite it. So we've got 1 over 2x to what power? Well, power of 2 root of 3. Rewrite that again. 1/2 x. Because we want to write it like this so we can use the power rule. And since 2/3 was on the bottom, it's a minus 2/3. Now we're ready to differentiate. Bring that negative 2/3 out front. So maybe what I need to do for you is, there's our negative 2/3. I've got the 1 over 2. And then I've got x to what power? I've got negative 2/3. I'm going to be subtracting 1, but I need a common denominator, so I'll be subtracting 3 over 3. So negative 5/3. A little bit of rewriting here. Okay, we've got a negative times a positive. We've got a negative. These 2's will reduce. So I've got 1/3. Now this x has a negative exponent, so the x to the 5/3 will be in the denominator. And then we'll simplify it a little bit. 1 over 3. Oops. 5th root of x and the cube root. Now that would be pretty acceptable, but you should know one other thing about this. This is the fifth power. If you think of this as x cubed times x squared, this part will come out even. So what we would end up with was 1 over 3x, because this comes out even when we take the cube root, and then the cube root of x squared. All right, what's next? I'll clear this again. Okay, where's my cursor? Here we go. Clear that. All right, so what have I got down here? Square root of 2x. I'm going to split this up. First of all, I'm going to rewrite this as square root of 2, square root of x. There's a trick for you. So we have square root of 2x to the 1/2. There's a rewrite that'll win your heart. Now I'm ready to differentiate. Bring that 1/2 out front. So I have 1/2 square root of 2 x to what power? You with me on this? Subtract 1 from that 1/2. Negative 1/2. Now what does that look like? Okay, first of all, we've got, if you take these two, you've got the square root of 2 over 2. Now what about the x? What you've got is x to the 1/2 power down here. Excuse me. And to write your final answer, square root of 2 on the top, 2 square root of x on the bottom. And if you wanted to, you could actually do this. You could make a 1/2. And since both of these are under the square root, you could make it the square root of 2 over x. I'm not too much a fan of that. I think I'd stick with this one instead. All right, let's go. So these are the answers they suggested. Should be the same as ours. Maybe a little bit different because I showed you some extra things. All right. Now this part, we're about the 2/3 way point in case you're interested. This is the part that is really simple because you would probably do this anyway. Notice what this is saying here is if you're taking the derivative of two functions being added together, you just take the derivatives separately and leave the sign there. If it's plus, leave the plus. If it's a minus, leave the minus. So, suppose you want to take the derivative of this. So you want y prime, and what you do is you take the derivative of 3x. We're going to write it like this. The derivative of 3x plus the derivative of 2x cubed. So all you need to do is work them out individually. The derivative of the first one is just a 3. The derivative of the second one, oops, what do I have here? Okay, 2x cubed. It's supposed to be a mark. So the derivative of the first one, the first function is 3. The derivative of the second one, bring that 3 out front, multiply it times a 2, and we'll get 6x. To what power? 3 minus 1 is 2, and there's your derivative. Very simple. You just take the derivative of each individual term. Keep the pluses or the minuses as they show up in your large function. And you can use that to any number of functions you like. In other words, you can have 7x squared plus 3x plus 5. Just take the derivative of each individual term and you've got the derivative for the big function. Sort of like this. If this function is composed of this one, and this one, just take the individual derivatives and you've got it. It's not a big deal. So, it says find the equation of the tangent line to the graph of this. First of all, you need the slope. Slope, derivative to the rescue. So first of all, work with this one. The first term, bring that 4 out front. 4 times 1/2 is 2. It's got a negative sign, so it'll be negative 2. And x to what power? Well, 4 minus 1 is 3. There's the derivative of the first term. On the second one, second term, bring that 3 out front. That gives you 9. Reduce that 3 right here by 1. You get x squared. And the last one, negative 2. There's your derivative. Also known as the slope. So the slope of this thing, negative 2x cubed plus 9x squared minus 2, depending on what x you're using. Well, we're interested in this particular point, and this point has an x value of negative 1. So what's the slope at negative 1? Just put the negative 1 in where the x's were. Negative 2 times negative 1 cubed plus 9 times negative 1 squared minus 2. What do we have? We cube the negative 1, that gives us negative 1 here, times negative 2 is a positive 2. Square the negative 1, we get a positive 1, times 9 is plus 9, and then minus 2. So the slope is 9. That's the slope for the equation that we're looking for. How do we find it? Remember our point slope form? Y minus y sub 1 equals slope x minus x sub 1. Just feed these coordinates in. We'll see what we get. Y minus, well, the y value is negative 3/2, so y plus 3/2 equals, the slope is 9, we already found that, and x minus the x value, x minus the negative 1 is plus 1. We've got our equation in draft form. So let's see what we've got. Y minus 1 1/2 equals 9x plus 9. Add the 1 1/2 to both sides. Y equals 9x plus 10 1/2, also known as 21/2. There's the equation. Now, the beauty of this kind of question is you can take your graphing calculator and graph this. So let y1 on your calculator be negative 1/2 x fourth plus 3x cubed minus 2x, and then let y2 be this tangent line, 9x plus 10 1/2, and what you'll see is you'll see this curve and you'll see this line tangent to it. Beautiful. When you've done all this work, you can see it coming to fruition. Okay, we went through all this, so we don't go any further. There's our slope. Here's our function, f of x, or g of x in this case. There's a tangent line, and you can see where the tangent line works with the original curve. Beautiful. And you've done it. That's the beauty of it. Not all equations work out that way. So how do you get that? Do just as we did before, using that point slope form. Can't emphasize that too much. It's very handy. Put the point in there and the slope in there and just clean it up. Looks like I might have had a typo. Well, you can check that for yourself. Okay, an application. Calculus is all about rate of change, and we're going to find the rate of change of the company's revenue with respect to time. So this is like y and x, except we're going to use r and we're going to use t. Now, if you feel more comfortable with y and x, you could just make a little note here. Let y be the revenue and let x be time t. And then when you're finished with the y and the x, you can put the r and t back in, and what you've got is a general formula. So here what we've got is the revenue in millions of dollars. Be careful about that. You saw something like that on the test too. And the model is revenue equals this, where t is in years. T equals 8 represents the year 2008. Instead of using 2008, it's easier to use just the 8. You want to know at what rate was the revenue changing in 2011. Well, if you want to know the rate, you want to find the derivative of that. But it's not going to be dy dx, it'll be dr dt. Get accustomed to using some different variables. The beauty of this is you can look at it and see what's happening. How is the revenue changing as time changes? Now, you know time is going to change in the positive direction, but this tells a small story. How is the revenue changing as time moves forward? So we'll find the derivative of the revenue model with respect to time. And there's our model, and there's our derivative. Need to go back to that. Multiply the 2 times the 22.766. Reduce this 2 to a 1. And then this, because it's just a t, this is the derivative for this term. And the derivative of a constant is 0. Oops. Sorry. There we go. So there's our derivative. This is how the revenue is changing with respect to time. In this interval, which remember represents the year 2008 to 2013. All we need to do, we want to find out what it was in 2011. So put 11 in where the t is up here. Put the 11 in there. And there we go. All you need to do is, I think this is a job for the calculator, don't you? 11 times 45.532. Yes, I think it's time for the calculator. So this is how the revenue for Buffalo Wild Wings is changing in 2011. And remember, this revenue is in millions of dollars. Millions of dollars. And all we need to do is, we just found the slope, which is the change in revenue with respect to time. And we're finished. Well, I hope you enjoyed the travel. You need some practice, but hang in there.